Hello everybody! In this worked example, we will show that the sinusoid presented in the lecture is indeed a solution to the differential equation for the harmonic oscillator. Similarly to the lecture, we will put our origin at the equilibrium position of our mass spring system, which is indicated by x equilibrium here. As given in the lecture, the solution for the harmonic oscillator is x of t, which is a times the sinus of omega t plus phi, with omega the angular frequency and phi the phase. We want to show that this is indeed a solution to the differential equation for the harmonic oscillator, and to show what conditions have to apply to omega in order for this to be true. Let's revisit the force balance of our system. On the left hand side of our force balance we have the sum of the forces or net force. On the right side we have the force of the spring. We can rewrite the left hand side of our equation using Newton's second law. The net force is given by the product of the mass times acceleration. The right side of our equation can be rewritten using Hooke's law. Hooke's law describes the force of a spring. It is given by the negative product of spring constant k times the distance from the equilibrium position. The negative sign here indicates that our mass always wants to move back towards our equilibrium position. This gives us m times a is equal to negative k times x for our final force balance. Also remember from the lecture that the acceleration is given by the second derivative of position with respect to time. Plugging this into our force balance yields the following differential equation, which you have seen in the lecture as well. Now, in order for us to show that the equation of motion is indeed a solution to this differential equation, we'll have to plug it into it. For this, let's determine the acceleration or second derivative of our equation of motion first. Let's start by determining our first derivative with respect to time. For this, we will have to use the fact that a derivative of a sine is always given by a cosine. Furthermore, we will also have to employ the chain rule. This is a derivative rule that allows us to calculate the derivative of a composite function, such as our equation of motion. In our equation of motion, the function f is our sinusoid and the function g is the argument inside our sinus, which is omega t plus phi. We can calculate our derivative in two terms. Our first term is the derivative of our function f, which is a times the cosine. Our second term is the derivative of our argument inside our cosine with respect to time. This adds a factor of omega into our final first derivative. This leaves us with omega times a times the sinus of omega t plus phi. Having found the first derivative, we can derive it again with respect to time to find the second derivative. We will employ similar rules as before. First, the derivative of a cosine is always given by a negative sign. Secondly, we will also employ the chain rule again. In similar fashion as before, the first term of our second derivative is given by negative omega times a times the sine, which is the derivative of the cosine of the same argument as before. Our second term should look familiar because this is again the derivative of our omega t plus phi with respect to time, which finally adds another factor of omega into our equation, leaving us with negative omega squared times a times the sinus of omega t plus phi for our acceleration. Now that we have found the acceleration of our system as a function of time, we can rewrite both sides of our force balance in order to see whether our equation of motion is indeed a correct solution. Starting from our differential equation, let's first plug in our equation of motion in the right side. This gives us the following. Next, let's do the same for our acceleration we just found on the left side of our force balance. This finally gives us this kind of complicating looking equation with loads of terms, which has to hold in order for our x of t to be a correct solution to our harmonic oscillator differential equation. Luckily, some terms cancel out on both sides. Firstly, the negative signs can be erased. Next, both sides also contain the amplitude a, which we can cancel out. And last but not least, the sinusoids in both sides of the equation are exactly the same, so can be cancelled as well. Do note, however, that if these signs were to have a different argument, they would not cancel out. This equation can finally be rewritten to m times omega squared is equal to k. Rearranging some terms gives us that the angular frequency squared is equal to the spring constant divided by the mass. We can take the square root of both sides to find that the angular frequency is either given by the positive or negative square root of k over m. In physics, however, we are only interested in real-life solutions. An angular frequency can never be negative, so we choose the positive solution for omega as our condition for it. Let's recap what we have found. In this worked example, we have taken a look at the harmonic oscillator, which can be described by the following differential equation. A possible solution to this differential equation is known as the equation of motion for our mass suspended on the spring. It is given by x of t, which is a times sinus of omega t plus phi. We have shown that in order for this equation of motion to be a correct solution to our harmonic oscillator, it has to obey some condition for omega. The condition it has to obey is that omega is equal to the square root of the spring constant k divided by the mass. Thank you for listening to this worked example, and I wish you good luck with your exercises.